Hi. Okay, so this is chapter 7. So what I'm going to do for each chapter from now on is I'm going to try to make a video for, first of all, for the lecture slides, and then secondly for the work problems. So as long as we stay online, for each chapter I'll send you the worked problems and the lecture notes, and they'll be in a separate category which I have under your assignments tab. So if you go on Eagle Online or Canvas or whatever you've got, go to assignments and you'll have a list of everything that's graded. And then if you scroll down, at some point you're going to come to a listing where it'll have videos. And under the videos for each chapter, you'll have at least one for lecture notes and one for work problems. For some of the 1412 videos, there will be probably more than one because the chapters are so long. And then also, if you look further, you'll see another topic for another assignment where you're going to see the PowerPoints and the work problems just as I've been sending them out to your emails up to this point. So, I mean, I don't know if I'm going to keep sending them in your email. I guess it'll depend on whether people are having problems getting to them on Eagle Online. If I can, I'll try to just go ahead and upload all of them to Eagle Online, Canvas. It's called Canvas for us, just so that you can go ahead and get to them whenever you need to. Anyway, so all of that stuff should be to you one way or another. And so what I'm going to do is I'm going to do this ad hoc. So what that means is that right now I'm recording prior to the week of, 23 March. So this is Sunday. So what I'm uploading right now will be what you'll need. For 1311, you have a test on Monday the 30th. So this is going to be for the 1st of April. So I'm kind of like trying to stay a week or so ahead. As far as these video recordings go, I'll probably go ahead and just upload all of your PowerPoint presentations at once. Anyway, so the good news is that we're starting off here with what's arguably the easiest chapter in the whole course. So once we get through this chapter 7, then we move on to two chapters that are a lot of like drawing pictures. And so like chapter 8 and chapter 9, there's not any math really. So and there's not a whole lot of math in this chapter either. So you can kind of give it a rest. And then once we get to the very last two chapters, we get back into the math. But hopefully by that time you'll have gotten your brain rested. All right, so chapter 7. Before I go any further, also, let me just say that there's been a problem with these videos, or whatever you want to call them. So what I'm actually doing is I'm doing a PowerPoint presentation, but it's recording the audio. So the problem is that I'm having is that when I click to go to the next slide, which I will in just a moment, it doesn't automatically do that for you when you're watching at home. So what you'll have to do, I think, is you'll have to manually click on the slideshow, maybe even 2 or 3 times in order to get it to go to the next slide. Once it switches to the next slide, then it should start to pick up again with the audio. So hopefully that'll work okay for you. That's a problem, and if I figure out a solution to it, then I'll fix it. But the way that these are set up is good because the file size is so small. So, for example, the last 2 videos that I did were only about 35 megabytes, which, I mean, Canvas can accept up to 500 megs, so I'm way under the limit. But if I started trying to put these on regular video, like something that you would upload to YouTube, and if I were doing it on a regular video recorder, the file size would probably be much larger. Just to give you a comparison, when I send these PowerPoints in PDF form to you, they're usually around 5 megabytes. So even a 30-minute presentation this way on PowerPoint is about 7 times that much. So it's still quite large. I mean, it's not the kind of thing you're going to send via email. But anyway, this is, I think, for right now, is the best way to do it. There's a little bit of a trick to getting these things open and getting the audio to work, which I will probably try to explain that to you in an email in the next half a week or so. Okay, so Chapter 7 is talking about what's called periodicity, so let's go ahead and go through it. I'm going to go through a slideshow that's much shorter than the one that I sent out to you in PDF form, because what I did was I just scarfed out the ones that I really needed. So that means there's only about 50 slides in this show as opposed to, I think, about 90 in the one that I sent out. So this one's going to be briefer, and we're just going to go through the points that you really need to know for the exam, and I'll try to go through those carefully. There's not really a lot in this chapter that's particularly difficult, but when we get to the areas that are difficult, then I'll let you know. So right now, I'm going to go ahead and click the slide to go to the next slide. And so if your audio stops at this point, it means you just need to click on the slideshow. Okay, so we're on the next slide. I'll try to let you know before I click so that you'll know to get ready to click yourself. So the big deal for Chapter 7 is periodicity. And what that means is that we're going to look at why it's called the periodic chart. And it's called that because every time you go across one row, oddly enough, adding another proton to a nucleus makes an atom completely different in some cases. In many cases. Just as one example of that, if you go from 1 to 2, from hydrogen to helium, you're going from a very reactive gas that can do all kinds of things to an inert gas that just kind of sits there and doesn't do anything. Sometimes the transitions between, for example, in the transition metals are not that great because they're similar, but most of the time, if you're in the main group elements, if you just move across from one column to the next one, then you're going to see that the properties of the elements change drastically. So anyway, every time you go across one row in the periodic chart, that's called one period. And then when you come back to the next row under that, like for example, if you go from the second row down to the third row, every element in the third row that's under that element in the second row will have similar properties because it has the same electronic configuration as the thing right above it. It has the same number of valence electrons. Just as one example of that, lithium is in the first column in the second row. Then if you came down one row below lithium, then you're at sodium and potassium. All of those are in a row, in a column. And they all have one valence electron, so that means that they all have similar chemical properties. And the reason is because chemical properties are determined by the electrons, by the outermost electrons. Because when atoms bump into other atoms, what bumps into each other is actually that outermost valence shell of electrons. So that's what determines the chemical property of, like lithium or sodium or potassium. So they're all similar because they all have one valence electron. So this slide says we're going to learn the basics of how the periodic chart is arranged. And the only way that I can make this show up is to go ahead and go across like I'm going to write something here. And it's extremely difficult for me to get this thing to do what I want it to do. So you'll just have to deal with it. Learning how the chemical properties of elements in the various groups tend to be similar. And remember that a group is a column, right? A C-O-L, a column, C-O-L, and that's the best I can do. So we call this periodicity, and that's why it's called the periodic chart, in case you were wondering. All right, so we also learned the basics of the chemical properties for some of these chemical groups. We're going to do 1 and 2 and then do 6, 7, and 8. Okay, I'm going to click. Next slide. Right, so here's the periodic chart, which you've seen before many times. So again, let's take a little peek at it. Remember that we kind of drew a line across here, and we said that everything over on this side over here is a metal, and everything over here is a non-metal. We're going to kind of tend to move hydrogen over here by helium for this purpose. Other times we'll leave it where it is, but for this purpose we want to move it over here. So we want to stick hydrogen right there. Things over here are clearly nonmetals, and things over here are clearly metals. And the things here in blue that are in the middle are called metalloids, which this may be the last time that I try to write a word because it's just a pain. Anyway, and it's really impossible. Metalloids. And I went through all that trouble to write this, and now you can't even read it. Let me go back here and try to make the E better. Okay, so metalloids. There we go. Still can't read it probably. All right, anyway. So the metalloids here are in the middle. Okay, so let's stop for just a second and look at this. Over here we say we have the metals, and over here we say we have the the non-metals. So in the middle, it kind of makes sense that we have things that are called metalloids. So, for example, if you look here, boron, silicon, germanium, arsenic, antimony, and tellurium and astatine are considered to be metalloids. Okay. Now there's another little thing that can confuse you here, so let's talk about it now because I've kind of got it on my mind. We can also look at this another way. So think about it this way. Metals tend to be conductors of electricity, also of heat, but mainly electricity, right? Because things like copper, for example, are used in wire. Most metals tend to conduct electricity, whereas things over here tend not to conduct electricity. So we could think of these things as well as being metals, even though we don't do it very often. We could call these things over here conductors over on this side, and we could call things over here non-conductors, which means that the things in the middle would be called semiconductors. And so if you'll look here at silicon, whoops, there we go, silicon and germanium also, and arsenic and some other things are used as semiconductors in things like computer chips. And the reason they're used is because they're not really conductors or non-conductors. They're in the middle. So you can do what's called a doping process where you make them so that they'll conduct under certain circumstances. And that's what you want. That's how they were able to reduce the size of circuits from large vacuum tube circuits to the tiny, tiny circuits that are used in like transistor radios and that kind of thing. So remember that if you can. There's really two ways you can look at the chart. You can divide it into metals, and you can divide it into non-metals. So the things in the middle would be metalloids. Or you can say things over here are conductors, and things over here are non-conductors, and things in the middle are semiconductors. So you might think to yourself, well, then are all metalloids the same as the semiconductors? And the answer is not really. Some of them are, and it depends on which source you read. But there are a few things that are, and I don't want to go into them, mainly because you don't need to know this, and also because I don't remember, but there are a few things that are considered to be semiconductors, and they're not metalloids, and vice versa. All right, so what we're going to do is we're going to look at the chart here. We want to remember that on this column here, the first column, we said that there's one valence electron, which I'll just try to write 1. So this column right here is one valence electron, all of these things, which means they all have similar chemical properties. And also, because they only have that one electron, they have a tendency, again, we're not really including H in this, because it belongs over here with helium. But because these things are in the first column, they have a tendency to give up that electron rather than to try to gain 7 more to get their octet. So we want to remember that. We want to remember that the things in this column right here are going to tend to give up their 1 electron that they have that's kind of like out there by itself. Another thing, before we go to the next slide, notice here that every time we come down to another one of these things in the first column, that we're coming to a new N number, a new primary quantum number, which means that we're getting bigger. So for example, if this is the nucleus and then if this is N equals 1, then when we come down to N equals 2, which would be lithium, beryllium, and so forth, then we're moving into this shell right here, this one. And so this one is much bigger than N equals 1. So this one is N equals 1 right here. This one is N equals 2. And then if we go to 3, then that's going to be way out here. And it's even bigger. So every time we move down a row, we're getting bigger. And so whenever we remove that outer electron, which we do in order to make a compound like sodium chloride, if we remove that outer electron, then notice what's going to happen is that we've removed the only electron in N equals 3. So the whole atom size, excuse me, will reduce drastically. Okay, and then the other thing over here in the 7th column, these things in the 7th column, and we won't go through every column, but in the 7th column, they tend to have an oxidation state of -1 because they have 7 valence electrons, and they want 8, and if they take 1 more to get 8, then they would have a charge of -1. So we say that their oxidation state is -1, and so they have a strong tendency to gain electrons, whereas the things over here in the first column tend to lose. Let's just write lose as best I can. This is really hard. Lose electrons. These lose and these gain ordinarily because they both want to get to 8. The ones on the left-hand side over there can get to 8 easier if they lose the 1 electron that they have. If we were in this column, they can get to 8 more easily by losing the 2 outer electrons. That would put, for example, if we just look at, let's take magnesium. Okay, starting with magnesium, if magnesium loses 2 electrons, it ends up back over here with neon's configuration of 8 electrons. Of course, it's going to have a charge of +2 now, right? So this one is going to wind up at +2. The reason is because it's lost 2 electrons, right? So it's got 2 more protons now than it has electrons. Okay, I'm going to click the next slide. So periodic trends, so let's go ahead and move to the next slide. So we're going to try to get a picture of how the various chemical properties change as we go up and down the chart and also as we move across the row. Okay, so the chemical properties, more importantly, will change as we go across a row. This is really the main thing here. They will also change slightly as you go down the chart, but that isn't something that we're going to worry about that much. The main thing that happens as you go down the chart is that the atoms get bigger and bigger because you're going from N equals 1 to N equals 2. Again, N is the primary quantum number, right? To N equals 3, and so forth for, whoops, you have to hit this thing just right, 4, 5, 6, 7. So every time you go from 1 to 2 or 2 to 3 or 3 to 4 or whatever, then these atoms are going to get bigger because you're going down to a larger main shell, and the main shells are the ones that are independent of each other. Okay, clicking to the next slide. So in this chapter, we're going to study four things: ionization energy, electron affinity, atomic radius, and ionic radius. And the difference between these two right here is that an atomic radius means that's the radius of an atom that's neutral, whereas an ionic radius would be like if you take an electron away from sodium, now you don't have Na neutral, you have Na plus. Or alternatively, you could take a chlorine excuse me, atom, and give it an extra electron, and now it's chlorine minus, not chlorine. So that's an ion. The chlorine minus is an anion, and the magnesium 2 plus or the lithium plus or whatever is called a cation. Positively charged ions are called cations, negatively anions. So these first two things right here, the ionization energy and the electron affinity, used to be averaged together to give something that was called, yikes, let me start over, electronegativity, which is going to be an extremely important topic, not only for this class, but also if you take 1412 or organic chemistry, you'll keep talking about electronegativity for the rest of your whole time in chemistry, whereas you probably won't really talk about this one that much after this chapter, or this one, but you will talk about this one a lot. So the way that they used to figure out what this thing over here is, the electronegativity thing, is they would take the average of this thing right here, the ionization energy and the electron affinity. They would average them, they would add them together, and then divide by 2. This one is actually a negative value, but they would take the absolute value of that. So we don't talk about electronegativity until next chapter, which will be chapter 8. So chapter 8, so we'll have to hold off on that, but it is also a periodic thing. So it's just like these four things right here. Clicking to the next slide. All right, so first of all, ionization energy. We want to learn what it is, and then we want to look at a couple of anomalies and then move on. The ionization energy for any atom is the amount of energy that's required to remove the outermost electron, or the highest energy electron, the one that's the hardest one, the one that's furthest from the nucleus, the one that's outermost. It's how much energy you would have to put in to pull it off of that atom. So every atom has electrons around it that is holding in place, and so in order to remove them, you have to exert a certain amount of energy. So you may be thinking, well, wait a minute, I thought that if it was in the first column that the electron just comes off. Well, it does, but it doesn't just come off because there's no energy holding it. It comes off because the amount of energy that's given off in the stabilization process is more than the amount of energy that you had to put into it in order to remove the electron. Like for sodium, it doesn't just come off. It is held in place. The outermost electron is held in place by a certain amount of energy. But if you expend enough energy to remove it, and then take that electron and put it into, for example, a chlorine atom, so that now the chlorine is going to be chlorine minus, the Na is Na plus, and then you have NaCl, then the amount of energy that is given off, or the amount of stabilization that you produce when you do that, is greater than the amount of energy that you had to input into the sodium atom to remove that outermost electron. So, but there is an energy, and so what we're measuring here is just the amount of energy that you have to put in to that atom to reach in and grab that electron off of that atom. So which ones do you think, I mean, just think about it for a minute. Look, if you have a chart, look at it, which ones would be the easiest to remove the outermost electron? Well, probably the things in the first column, right? So it would be things like sodium and potassium. And then next probably would be the things in the second column, right? Which they're going to be a little bit harder, but they're still going to be easier than anything else in the chart. So the easiest would be the things in the first column, and then the next easiest would be the things in the second column. And then the hardest ones would be the ones in the seventh column, because they really, really want to hold on to the electrons they have. And in addition to that, they also want one more electron, right? So it's going to be very difficult to get rid of an electron off of something in the seventh column, like fluorine, chlorine, bromine, or iodine. And then a little bit less than that would be things in the sixth column, like oxygen and sulfur. So the hardest ones to remove from would be these in the seventh column, and then next hardest would be the ones in the sixth column. Now we left out 8, and actually 8 would be even harder than 7, or maybe harder. It's actually kind of hard to say. Both of these would probably be so difficult to remove the outermost electron that they're basically about the same, because they both hold on with a lot of force. So the last 2 columns, but we aren't really that worried about the 8th column, because we don't really do that much chemistry with it, because it doesn't do much. Okay, so the amount of energy that's necessary to remove the outermost electron from an isolated neutral atom. And so here they're showing that for hydrogen, it's over 1,000 kilojoules per mole. Next slide. So this is just here at the top is just a repeat. The ones that are going to be the easiest to remove the outermost electron would be the group 1, the alkali metals. So that's sodium, potassium, lithium, and so forth. Francium, cesium, rubidium. And that is, if you'll look down here, is because that one valence electron in the S subshell will be the only electron in that level. In that N level, it's the same thing we just said. So when we remove it, the atom actually becomes more stable. So it's actually kind of glad to get rid of it. Next slide. So, and then the hardest ones to remove, as we also just mentioned, will be the noble gases and then the halogens. Next slide. So it's easier to see this if we look at a chart. So if we notice here, this y-axis is showing how much energy we have to put into these atoms to get that outermost electron off. So the way this works is this right here is hydrogen, if I can get this to work. And then, of course, this is helium here. And then down here is lithium, beryllium, boron is over here, boron, carbon, nitrogen, oxygen, fluorine, and then neon is up here. Okay, let's take a look just at this row right here, which I'm going to just draw a circle here. Starting down here with lithium. So we noticed that the easiest one is the one in the first column, lithium. So lithium's in the first column or group. And then if we move up to the next one, it seems that it's a little bit, so this one right here is beryllium, and it's a little harder to remove that electron. Notice that this one right here is a little higher. It doesn't seem to be going in the same kind of a linear pattern with these other ones. I hate to mark this, because once I mark so much you can't see it anymore, but if we look at this kind of like pattern here, it's pretty much linear. But we have an anomaly right here, and we have another anomaly right here. So, but other than that, if you'll look at it, you'll see that it kind of goes up, up. I mean, forget that one, up, up. Forget that one, up, up. Basically, it goes up. So we're going from so this is going to be, here's the first column, here's the second column, the third column. Again, I'm trying not to make these marks too big. Fourth column, fifth column, sixth. I'm trying to not make these marks too big because then you can't read it. And then eighth. So we went from 1, 2, 3, starting at the bottom, 1, and then just going up 2, 3, 4, 5, 6, 7, and then 8. And basically, with a couple of exceptions, which I'll explain, we're going from the lowest to the highest energy, right? Can you see that? So it's kind of linear. The more rows you move across to the right on the chart, the higher the energy required to remove the outermost electron. Okay, so that's the general rule. Let's take a little look now at why we have these exceptions. So starting right here, that's beryllium. So if you have a chart with you while you're watching this, if you take a look at the chart, you'll see beryllium is in the second column. All right, so there's an exception here because beryllium has a filled s suborbital. So it's in the second main row, and we've already talked about how that things are stable if they have 8 valence electrons, but there's also a certain amount of stability in things that have a filled subshell, like, for example, the S subshell. Usually it's the S subshell that we're concerned about, because if the P subshell is full, that means you've also got an octet. So usually we talk about when something has a full S subshell. So that's stable to some extent. It's not like having an octet, but it's like something that's less than that. So it's a little bit stable. It's not real stable like an octet. And then there's another thing that is a little stable but not completely stable like an octet, and that is when you have something that's half full. In other words, and usually this one is going to be dealing with the p orbitals. Now remember, there are 3 p orbitals, which I've been calling px, py, and pz, and each can hold 2 electrons for a total of 6 electrons in the p orbitals. That's the last 6 columns over at the far right hand side of the chart. So in the second row, it would be BCNOF and then neon. So the third little rule that you might want to remember, or you should remember actually, is that when you have the p orbitals one half full, then that's somewhat stable also. Not as stable as a octet, but somewhat stable. It's a less stable thing than an octet, but more stable than anything else. So if you want to look at it in a kind of a hierarchy, the things that are less stable would be a full S shell. In other words, the 1s and 2s, or the 2s and 2s1 and 2s2 columns are full. So that's anything in the second column basically. And then also a half-filled P shell, or P subshell. So that would be anything in the 5th column. So that's going to be things like nitrogen and so forth. All right, so notice here that we can now understand why beryllium here, I'm kind of running out of room here to draw, but this thing right here, beryllium, the reason that it's harder, the reason that this dot is higher here is because beryllium has a full S subshell. So it's harder to remove that electron than we might have anticipated. Come up now here, the nitrogen here is a little bit harder to remove because it's stable, because it has a half full P subshell. It has 3 P electrons, Px, Py, Pz, and they're all going in by Hund's rule, which is spin up, spin up, spin up. So that's a stable environment. The next one over here, which is the oxygen right here, will actually be easier to remove the outermost electron, because if you do remove it, then you're going from having 4 p electrons to 3. In other words, you're putting oxygen back like it would be if it were nitrogen. And nitrogen has 3 p electrons. It's half full in its p subshell. Well, oxygen would be the same way if it lost 1 electron. So it actually kind of like wants to do that for the same reason here that, this one here would do the same thing. So lithium beryllium. So boron here, if I can get this to work. So boron here would also do the same thing that oxygen here would do. It would be more likely to give up an electron because that allows boron to go back to this more stable environment that it would have if it had the same electronic configuration as beryllium. Here, up here, oxygen tends to give up that 4th p electron because if it does, then it would have 3 p electrons and therefore be more stable. Okay, so let's just review for a minute. Basically, as we go, and let me use this one instead, as we go from sodium to argon, basically these ionization energies are going to increase in a linear fashion, with a couple of exceptions. This one right here is going to be lower than we expected because if it gives up 1 electron, it will end up here at a half-filled p orbital. And this one right here will be harder than we expect because it has a full s orbital, suborbital. So the 3 rules for ionization energy: number 1, as you go from left to right across the chart, it gets harder to remove the outermost electrons, so the ionization energies go up. Rule number 2, if you're in the second column or group, the electrons will be harder, a little bit harder to remove than you would have expected. And the third rule is that if you're in the 6th column, the electrons will come off a little bit more easily than you would have expected because that causes them to revert back to the 5th column configuration. Okay, next slide. So we've already talked about this. Let's just go ahead and move down to the bottom here because this stuff up here, we've already treated this. So the main order of stability, the most stable thing that you can have is a filled octet. In other words, something in the 8th column. Then a filled subshell, and specifically we're usually talking about S here. Not so much the other things. And then a half-filled subshell, and here we're talking usually mostly about the P's. All right, next slide. And so we've already talked about this. We've already said that group 6 tends to be lower than we would have expected because that puts them in the same electronic configuration as group 5. So this one is going to be lower than we would have expected. Next slide. So here again we're seeing that 2A is higher than we thought down here. This is for beryllium. You can really see it here more so in the first period here. And then in the second period from lithium up to neon here, we see here the beryllium is higher than we thought it would be. And the oxygen here is lower than we thought it would be. Next slide. This slide is actually showing what happens, though, if you try to go into, for example, for sodium, if you try to remove more than this first electron. So the first one here comes off easily because it doesn't really mind if you take it off because it kind of wants it to come off anyway. But once that 1 electron right there comes off, then sodium reverts back to the previous row's 8th group or column. In other words, it reverts back to the same electronic configuration that previous noble gas had before it. And so, in other words, it has an octet at this point, so it's stable. So it doesn't want to give up any more electrons. And you notice here that in order to remove another electron down here would require about 10 times as much energy as the first one. You're going from about 500 to about 4,600. So the first one comes off easily here, but the second one won't. I mean, it's really, to be honest, it's almost impossible to get that second one off. Now, obviously, there's a way they did it because they were able to measure the energy here, but it's very difficult. For magnesium, magnesium is in the second column or group here. You can take off 2 electrons fairly easily. This one and this one come off fairly easily. At that point down here, as you go here, you've removed 2. Now you've gone back to the octet of whatever the previous noble gas was in the previous row. So in other words, the magnesium, when it has a 2+, has an octet. So anything after that, starting right here and going further down, will be, again, very, very difficult to remove. Notice it jumps from 1,400 here to 7,700. That's a lot more. Aluminum is in the third column, so you can remove 1, 2, 3 fairly easily. But after that, it becomes much more difficult because you're removing octet configuration electrons from here all the way down. And then the fourth column, silicon carbon, you can remove 1, 2, 3, 4. Not too much trouble, but then after that, look what happens. It's jumping from 4,000 here all the way up to 16,000 here. The fifth column would be N, and then P below it, and then so forth. So the fifth column means there are 5 valence electrons, which means that you can remove 1, 2, 3, 4, 5, and actually to get to the fifth one, to get the fifth one off is a little difficult. And then you've gone back to the octet from the previous row, and notice the change here is really drastic. You're going all the way from 6,000, these are in kilojoules per mole, to 22,000. So you're going from 6. And then you have the same thing happening here in the next row, and the next row here, and then the next row here. So this is the pattern. Next slide. All right, next thing we want to talk about, so we're finished with ionization energy. We want to talk about something that's called electron affinity. So electron affinity is defined as the energy that's released, not the energy that's required, but the energy that's released. So what that's telling us is that we're going to something that is more stable than it was before. In other words, when it takes an electron, so let's just hold on for a second. Let me just write this. And I'm going to just probably stop after the B so that we don't take too much time. More stable. So here, what we're doing is we're making something more stable. Whereas in the ionization energy, we were actually doing the same thing, but we had to actually exert energy to get an electron to come off. Here we don't. So we don't have to put energy in. The reason is because what we're doing is we're taking something like chlorine, which is neutral, just an atom, and we're adding an electron to it. And we don't have to put any energy in, because when that chlorine sees that electron, it's going to grab it, and it's going to become chlorine minus. And not only does it not require energy, but it actually gives off energy. And that's because this thing right here, is more stable than what we started with back over here. It's more stable. So that means that it's at a lower energy. And that means that energy has been, if you've gone from a higher energy state to a lower energy state, something had to happen to the energy that was the difference between the two states, and that's usually given off as heat. So what we're doing here for the electron affinity is we're measuring how much energy or heat is given off when we drop an electron around a chlorine, and it changes to chlorine minus. All right, so this is actually, if you look at it in terms of the amount of energy that's required to remove it, this is not that, it's the opposite. It's energy that's released, so they give it a negative sign. So this is negative. It's a negative value. So I'm going to go ahead and move to the next slide now. So notice here in the Y column, the Y-axis rather, we've got negative values, not positive values. So the higher up these things are, like fluorine is way up, the higher up they are, the more energy is released. In other words, the more stable they are. So for electron affinity, and you'll have to remember these names, electron affinity means that it is the amount of energy that's given off by a neutral atom when it gains an electron. And it only really applies, mainly it applies to things in the 7th column or group, which are the halogens, and the things, maybe to a lesser extent, the things in the 6th column. And then to a much less extent, things in the 5th column. Maybe if I do this the whole semester, I'll get better at it. And it doesn't really apply to anything else. So if you look here, this is the 7th column here. This is the 6th column here. It gives off less energy because the things in the 6th column are not quite as desperate to get one more electron as the things in the 7th column. And then this is the 5th column here, down here. This one right here, nitrogen, is in the 5th column. You can see it's at 0. So in that particular case, the 5th one doesn't really give off any energy at all. It's basically going to have the same stability that it had before. So fluorine, a lot of energy is given off. The one before that, which is oxygen, gives off a sort of an intermediate amount of energy. And then the nitrogen and everything below that don't really give off that much. Carbon gives off a little bit. And then boron gives off just a tiny amount. If we move to the next row, we see that the thing in the 7th column, again, gives off a ton of energy because it really wants that extra electron. The thing in the 6th column gives off less here, but still a significant amount. The 5th column, significantly less. The 4th column, a little more. The 3rd column, less. And then by the time you get down to magnesium here in the 2nd column, it's 0. So really, if we look at it, we can see that mainly what we're dealing with, things in the 7th column, the halogens, these 4 things right here, these are the things that we're mainly talking about with regard to electron affinity. And then to a lesser extent, the things in the 6th group. Okay. Now, there is an anomaly here for carbon, and the reason for that is that if carbon gains an electron, it has a half-filled p shell. So carbon has six electrons, of which 4 are valence electrons, and that's 2 that go into the 2s. So it's 2s2, and I'm probably not going to be able to make this happen, but 2s2, and then it's 2p2. I must be getting a little bit better at this. Okay, so 2p2. So remember that if you have 3 electrons in your p subshell, it's half full. So in other words, if carbon gains 1 more electron, then it's going to be going from 2 to 3, which would be a half-filled p suborbital, which means that carbon would be more stable if it did take 1 more electron. So it kind of like wants that 1 extra electron more than we would have expected, because if it gets it, it's more stable. So that's why it's going to give off more energy here than it would, otherwise than we would have expected. Next slide. Okay, number 3, atomic radii. So what we're talking about now is the way that atomic radii compare with each other. And so we're talking about only when they're not charged. We're talking about when they're neutral atoms. So if we draw a chart here just in general, and we'll look at this again later. So here's a chart. Basically, as we come down the chart, anywhere in the chart, in any column or group, as we come down the chart, obviously the atoms are going to get bigger. B, I, G, G. There's got to be a better way. Bigger. Okay, as you come down. So, and that's true anywhere in the chart. Anywhere. Because every time you come down 1 more row, you're adding another complete shell, another n number. Okay, so I'm not going to draw any more arrows down. So that's one rule, and that's this one. That's the one here at the bottom, in increasing size as you go from the top to the bottom. The other rule is harder to understand. This one's easy. This one down here is easy to understand. The one that we're going to do now is harder to understand, and that is that as you go from left to right, the atoms are going to get smaller. Okay, let's just write SM. That stands for smaller. This is harder to understand. Let's go ahead and go to the next slide. So we can see here, basically as we go from lithium, let me put the mark up here, so from lithium to sodium to potassium, rubidium, cesium, francium. Okay, as we go across the line I just drew here, we're going down the chart in the first column. So if you look at a chart, look at the first column. It's going to have lithium at the top, sodium's in the second row, potassium, rubidium, and so forth. So as we move down the chart, notice these things are getting bigger. And that's according to the y-axis here, which is showing the different sizes. So that's the first rule. The second rule, notice here that every time we come to the beginning of a new row and go down, or I'm sorry, go across the row, that the size goes down. And that's a little harder to understand. So notice this is the second row here, the beginning. The third row starts with sodium, and as we go across the row, the sizes are going to increase. Okay, I'm going to flip to the next slide, and I'm going to have to take a break for a second. I'll be right back. Right, okay, so I'm back. Um, the next rule is that as we go from left to right across the rows, that the things are going to become smaller. So the rule that is, the rationale that is given here is because the electrons that are in the same shell do not shield each other. So let's take a little look at this, because this is the hardest thing to understand in this chapter. So what they're saying is that as we go out, and I'm going to draw this up here at the right, here's the nucleus of an atom. Here is n equals 1, and then here is n equals 2, and I think we'll stop here because I'm running out of room. So what they're saying is that when you first put your first electron here, there's the first electron in the second row, so this would be lithium. Notice that the things here underneath it are going to shield it from the protons in the nucleus. And there are going to be, first of all, 3 protons for lithium. Here, there's going to be 3 protons and 3 electrons. So the 3 protons here in the nucleus will draw this outermost electron a little bit less, because these 2 electrons in the first shell, the 2 in the 1s shell, 1, 2 here, are going to shield, down here, shield this outermost electron here from the nucleus here. Now, don't worry too much about it if you don't see this, because we're going to go through it again. So then these are actually acting as a shield. There's 1 electron right there, which you can't see very well. And here's the second one. And then we're moving from 1, n equals 1, to n equals 2. So when we put 1 electron out here, and we have 3 protons in the nucleus, then we're in lithium. If we put another proton now, and I'm not going to keep drawing the protons, but this is going to become beryllium. And now we have 2 electrons out here in the second shell. But notice that the shielding is not going to be any more than it was for just the first one, because these 2 electrons, this one right here and this one right here, are the same distance away, and they don't shield each other. So that means that because we've added 1 more proton here in the nucleus, then we're going to have an effective charge on the second electron that is greater than it would have been on just the first one, because these last 2 electrons don't shield each other. This one right here and this one right here don't shield each other. And then if we add a 5th proton, so that would be what is it? Boron. So we would have 5 electrons at this point. Let me think about it. For that, is that right? So it's hydrogen, helium, lithium, beryllium, boron. Yeah. So for boron, we would have 5 electrons and 5 protons. Again, though, notice here when we add this 5th electron, now we have more protons, so we have more of a positive charge here in the nucleus here. I don't know if you can see that. But this electron that we just added here is not shielded any more than this one or this one. In other words, the effective charge that these 3 electrons now feel from the nucleus here is actually going to be more than it would have been if they had been going, for example, if we had put the 3rd one in this shell, and then, for example, if we had put the 4th one in this shell by itself, and then put the 5th one in this shell further away from the nucleus by itself, then this one right here would be shielding this one, and this one right here would be shielding this one. But that isn't the way it works, because we're actually going to wind up putting not only these 3 here that we have in the 2 shell, but we're also going to put 3 more. So we're going to wind up with a total of 4, 5, 6, and none of them are going to shield each other. So that means every time we add another proton to go along with these added electrons, we're increasing the positive charge, and that's going to draw the whole set of electrons here and 2 closer together, and also closer to the nucleus. And that means the size of the atom is going to get smaller because it's these outermost electrons that determine the size, right? So in other words, the size of this atom right here, this one, the size of that will be determined by the outermost row of electrons or shell, not by the nucleus and not by the first shell, but by the outermost shell. In this case, that would be 2, but that will grow smaller. It will move in every time we add another proton, because even though we're adding electrons also, that isn't going to make any difference as far as the size, because the electrons are not shielding each other from the protons. So in other words, basically what it boils down to is this: every time you add another proton electron pair, it's going to get smaller, because it does make a difference in the size when you add the proton, because you're increasing the positive charge. But it doesn't make any difference as far as the size is concerned when you add another electron. So the way that they say that is they say that the effective charge that the electrons fill is going to be greater the more protons that you add and the more electrons you add as you go across a row. This Z effective thing that I'm writing right now, that's the symbol that they use for Z effective. That means the effective charge that the electrons are actually feeling, F-E-E. So this is the effective nuclear charge from the nucleus. I'm not going to keep running this because it's going to take forever. It's the effective nuclear charge. The effective nuclear charge will increase as you go across the row on the periodic chart. So as you go from left to right across the chart, the effective nuclear charge, in other words, the charge that these electrons in the outermost shell feel, will be larger and larger. Next slide. So what happens is that, for example, in the second row here, they start off with only this one electron, and we have one more proton. So it's going to be populating a new shell. So it's going to be bigger than the one that would have been above it, which would be this one right here. This is hydrogen. But then more and more, as you add more and more protons, you're just increasing the effective charge that the electrons are filling, F-E-E-L-I-N-G, which means that the atoms will get smaller and smaller. Now you can see here, you can actually see it a little bit better if you look. Well, actually, none of them are perfect. These are not perfect. So if you look at the line I just drew, you can kind of see, but again, it isn't perfect, but they're basically getting smaller and smaller as you come from left to right, but not completely. Like if you look at these numbers here, 248, 215, 167, 140, 140, this one right here goes back up just a little bit, 133, 131, but basically, as you go from left to right, as you go from here over to here, in any row, the size will get less and less. It actually does work here in the second row. So not by very much. From here, or actually even from here to here, it doesn't decrease very much, but it does decrease. All right, so you've got two rules here. And if you look at this picture right here, notice that as we come down the chart, in any of these columns, the size gets larger. It doesn't matter if you do this column or this column, any of them. The size will get larger. And then as we move from left to right, the size gets smaller. Okay, so this is the most important stuff that you'll need to know for this chapter, but there's a few other things we need to talk about. So I just switched the slide and I forgot to say it. So this slide right here we've already talked about, so I'm going to click another slide. And here's another picture of what we just talked about. I'll let you look at this on your own because this is getting long. So let's go to the next slide. And then this was a little graph that just shows you that in this blue line here, the effective nuclear charge is actually increasing as you go across a row down here at the bottom. You're starting with sodium and you're moving from left to right across a row. The charge increases, it goes up. The radius decreases or goes down. Next slide. So we have a little exercise here. Arrange oxygen, fluorine, and sulfur according to increasing ionization energy and size. So let's just draw these three. So I'm going to try to make a little part of the chart here, and we'll look at these. So this is going to be sulfur, oxygen, fluorine. Fluorine is in the 7th column. Okay, so first of all, let's do the size. The smallest one is going to be fluorine because it's all the way to the right and it's also further up. Can you see that? So if we go from smallest to largest, this would be the smallest, and then this one, and then the sulfur will be the largest because it's in the next row down. As far as ionization energy, that's saying or asking us which ones are going to have the hardest electrons to remove. Well, the sulfur will be the easiest here, and that's because it's further down, it's larger, and so its valence electrons are further away from the nucleus, so they're not held quite as tightly as the ones in the row above it. So the easiest ones to remove will be the ones in sulfur, and then the ones in oxygen, and then the ones in fluorine are going to be the hardest to remove. So for ionization energy down here, from smallest to largest, it's going to be sulfur, oxygen, and fluorine. Okay, next slide. Whoops. There we go. All right, next, and this is the last thing we're going to do in this chapter for periodic properties, ionic radii. The difference between this and what we just talked about with atomic radii is now we're talking about what we would have if we took either an electron off of a metal or put an electron onto a non-metal. So first of all, let's do the metals. Metals tend to give up electrons, right? Remember things in the first and second column in particular, they want to get rid of either 1 or 2 electrons because they get an octet that way. So let's compare the size of a neutral lithium atom with a lithium ion where it's given up the electron. Notice the lithium ion here is much smaller than the lithium atom because it's completely lost that outermost shell. So like if that's the nucleus and that's n equals 1, then the lithium would have had this n equals 2 if it had that electron right there. So it would be a lot bigger. Remember, this is going to be the size of the atom. Here, the outermost part is going to be the size of it. But if we take away this electron right here, then it's going to collapse back down to only having these 2 electrons. This one and this one. It'll have the same configuration as helium. So the size will go way down. So that's what's happening right here. This one is much smaller. Same thing for this one, and this one, and the other 2 here. And then you also have another factor, and that is that when you take away an electron, in addition to the fact that you're losing this outermost shell, you're also going to have more protons than you have neutrons. Notice you've got this plus charge on all of these. So that also makes these ions, these positively charged ions, which are called cations, are going to be a lot smaller than the neutral atoms. So the trend here is that if you have a metal and you remove the outermost electron, then the ion is going to be very much smaller than the original neutral atom was. So that's the main rule you need to remember here. In the second column, the beryllium, magnesium, calcium, and so forth there, these are all in the second column. So what they're doing is they're removing 2 electrons for these. So you're going to have 2 more protons now than you have electrons. So obviously, these are even going to be smaller. So here again, you're also having the same effect of losing this outermost N shell. But in addition, now you have 2 more electrons. I'm sorry, you have 2 more protons than you have electrons. So there's even a more dramatic effect here. Next. Okay, the other possibility for ions would be, for example, the 7th column, the 7th halogen column, but that's the opposite. So in that column, the elements tend to gain an electron to become an octet, to have an octet. So, for example, fluorine gains an electron and becomes F minus. Now, this is the opposite situation. So instead of getting smaller, the ions here, which are called anions because they're negative, are going to get bigger. And the reason is because now you have 1 more electron than you have a proton. So you have an extra negative charge, and that tends to make the electrons push each other out more. So if you have a shell like that, and you add 1 more electron to it, then the shell might look more like that. So you can see here that the effect is that when you add an electron to something in the 6th or especially the 7th column, that they get bigger. So anions get bigger. So the rules here, anions get bigger, cations get smaller. Next. So here again we have a picture of the chart, which I'm going to go next. I'll let you look at that on your own. Next here. So I'm just going to read this very briefly because we're kind of like out of time. So this is just discussing, this is taken from your textbook. Metals exhibit the shiny luster we associate with, like, for example, copper or gold or silver. They conduct heat and electricity. They can usually be bent up into whatever shape you want to bend them into, or drawn into wires, which that's called being ductile. And then that's about all that we really need out of this. Let's move now to the next slide. Metals tend to have very low ionization energies. What that means is that it's easy to remove their outermost electrons for reasons that we've discussed many times. The first ionization energy is usually the best indicator. So in other words, if you have a first ionization energy that's low, then it's probably a metal. If you have a first ionization energy that is high, it's a nonmetal. Next. All right, now nonmetals, they can be solid, liquid, or gas, and they are. Whereas metals are typically solids. Nonmetals are not lustrous and are poor conductors. Also, in the nonmetals, 7 of them exist as diatomic molecules. In other words, things that join together in pairs because that fulfills their need to have an octet. Things like H2, N2, they exist as H2 and N2, and O2 and F2 and Cl2, rather than just H or N or O. Because they don't have an octet just as H or N or O, but if they join together as a pair, they have an octet. They both do. Of these over here are all gases. Whoops. And this one right here is a liquid. And iodine is actually a solid. So we have all 3 different states. Next. They tend to have, so nonmetals tend to have very large electron affinities. They really want to take on another electron. So they tend to gain electrons. Metals tend to lose electrons. So when we add this metal to this nonmetal, the metal here will donate its electrons over to the nonmetal, and the nonmetal here will become Br minus, and the aluminum will become aluminum 3 plus, and you wind up here with 3 bromines that are attached to 1 aluminum. This is actually an ionic compound, right? So this is not covalent, it's ionic because you're dealing with a metal here joining together. So a metal here joining with a non-metal. Okay, next. Metalloids, we've talked about this just a few minutes ago. Actually, now I guess it's been more like about 45 minutes ago. Metalloids have properties that are intermediate between those of metals and nonmetals. So they may have some characteristics of each. Next. Okay, so let's go through very quickly some of the different characteristics of different groups. So next, the first column is called the alkaline metals. And so what I'm going to do is go through the highlights that you should know for your test, because you could see these on a test. The first column is going to be, we already know this, and we can also find it by just looking at the chart. The things that we need to remember: they're the most chemically reactive of the metals because they would only have to give up 1 electron. So they really, really want to give up that 1 electron. So that means the same thing as to say that they're very reactive. Can you see that? Because they really want to give up that 1 electron that they have in that outer shell, that makes them reactive. So they tend to react with nonmetals, which we've talked about that about 1,000,000 times. They can also form oxides, and what that means is that they can join with oxygen to make things like magnesium oxide and that sort of thing. If you go down this group right here, the ionization energy will get smaller because the outermost electrons are going to be further from the nucleus and less tightly held. Obviously, the radius is going to increase, and this is true for all 8 groups that we talk about. And then you don't really need to worry about this stuff right here, because you're probably not going to ever see that on a test. Next. So we need to remember that because they want to try to give up that 1 electron, remember when something gives up an electron, it's oxidized itself. And let me say that again. If something gives up or loses electrons, it's being oxidized. That is equivalent to saying that it's a reducing agent. So don't let this confuse you. A reducing agent is not being reduced itself. It's reducing the other thing. It's being oxidized itself. And I'm not even going to try to write that out. I'm just going to put OX for oxidized. It is being oxidized. It's losing electrons. But the other thing is gaining electrons, so it's reducing the other thing. So that's why it's called a reducing agent. So try to remember that group 1A, powerful reducing agents, metallic, obviously, because they're on the metal side, good conductors of electricity, very reactive, and they occur only in salts. So these things here that have these red asterisks are the things that you should remember for the test. Next. Hydrogen does not properly belong to any group because it has some traits of a metal and some of a nonmetal. Usually occurs as a colorless diatomic gas. Extremely important in everyday chemistry. Next. Has a much higher energy than we would expect. You don't need to know that. It can share its electron with nonmetals to make covalent compounds like water, H2O. That's covalent. On the other hand, it can also donate its electron and become H+, which means that it's making an acid. Like, for example, with HCl, the H electron comes off the H and becomes part of the Cl. So you have H+ and Cl-. And when you have H+ and Cl-, you have a very strong acid called hydrochloric acid, which you can mix in water. So that's another thing it can do. It can make covalent bonds, or it can make acids, or it can also make ionic compounds, although that isn't something that happens a lot. So, and it happens in kind of a weird way, where the H actually, instead of losing an electron like it does here, it actually gains an electron and makes H-, and then it can make something called a metal hydride. You don't need to probably worry too much about that one. Next. 2A. So these are going to be reactive, but not as reactive as the things in the first column. So these are not called alkali metals, they're called alkaline earth metals. That's the name of the column. Beryllium, magnesium, calcium, strontium, barium, radium. And they tend, again, like the things in the first column. So they're chemically reactive, but not as much as the things in the first column. And like the things in the first column, they tend to react with nonmetals to make ionic compounds, like magnesium chloride, and also oxides like magnesium oxide. Okay, as you go down the group, as you go down the chart this way, the size, again, as always, gets bigger. So the atomic radius will increase. And the ionization energy will get smaller because, again, the electrons in the outermost shell are further away from the nucleus than they were before. So it's easier to pry them loose. So it takes less energy to get them off. So the ionization energy decreases. And for the same reason, the reactivity increases, because since it's easier to get that outer electron off, it makes it easier for it to react, because by definition, when you take off that outer electron, it's probably going to be because it wants to react with something like chlorine. And don't worry about this last thing here. All right, next. So for the 2A, things in the second column, they're good reducing agents. That means they're oxidized themselves. In other words, that means they lose electrons themselves fairly readily. Not as much as the first column, but still fairly readily. Again, obviously, they're metals, malleable, silvery, which you can remember that if you want to. They're good conductors of electricity, and they're very reactive, but not as much as group 1, but still very reactive. They occur in salts, ionic compounds, and oxides, like, for example, calcium oxide or magnesium oxide. And they have the second lowest first ionization energies, next only to things in the first column. Let's finish this up now. Next. Sixth column, next. This is going to be oxygen, sulfur, selenium, tellurium. So as you move from oxygen at the top of the chart down to livermornium at the bottom of the chart, the things down at the bottom here are actually metals. The things at the top are nonmetals, and the things in the middle are metalloids, or semiconductors. Okay, so this is the only column we've seen so far. Remember, the chart looks kind of like this, and then you have metals over here, and you have nonmetals up here, and then there's a kind of a line that goes right through the sixth column, which is the column that we're dealing with here. And it goes right through the middle, dividing between metals over here and nonmetals over here. So the things at the top up here in the sixth column are non-metals, and the things at the bottom are metals, and the things in the middle are metalloids. So these things right here are metalloids, These things right here are metals, and so forth. Okay, these are also very reactive in the reverse sense that things in the first two columns are reactive. Here it's because they want to gain electrons, because if they're in the sixth column, they need 2 more electrons to get to 8, which makes them reactive. Especially this one, and maybe less so the other ones. Again, as you go down the group, the radius gets bigger, and this is true for all columns. Don't worry about this. So let's mark it out. And also the electronegativity, we haven't talked about that yet, so you don't know what it is. But basically, it's just how strongly these atoms attract electrons. So as you go down these columns, the electronegativity decreases, and that's true again for all the columns. And the character here changes from a nonmetal to a metal next. So what you should remember is that they tend to be reduced themselves. They tend to gain electrons themselves, or you can also refer to them as being oxidizing agents because they oxidize the other thing. So whatever the other thing is over here, they are going to oxidize it. In other words, they're going to make it, this thing over here is going to have to lose electrons, and the electrons are going to come over to the thing that's oxidizing them. So they're powerful oxidizing agents. So for your test, this is a good time for you to try to really get it straight in your mind, the difference between being oxidized and reduced. So try to remember the definitions for oxidation, reduction, and then also oxidizing agents, and reducing agents. So try to get that straight now while we are doing an easy chapter, so that you don't have to worry about it later when we get back into the harder stuff. So when something is reduced itself, it is the oxidizing agent. And when something is oxidized itself, it is the reducing agent. Okay, non-metals at the top of the sixth column, like O, metals at the bottom, metalloids in the middle, and then here oxygen is a gas, right, which you know that. Everything else in the sixth column is a solid. And another thing you should know for this column is that everything in the sixth column is a poor conductor of heat and electricity. They're very reactive because they only have 6 electrons and they want 8. You also might remember these last two things here. Selenium is a semiconductor and sometimes considered a metalloid, and tellurium, both of these are in the sixth column. Selenium and tellurium. Tellurium is also a semiconductor and a metalloid. Next. Okay, I'm going to talk just a little bit about metal oxides, and then we'll talk about non-metal oxides. Metal oxides, and let's just look at this example at the bottom here. And this is the only one I'm going to look at. Calcium is a metal, so when it makes an oxide, and if you're wondering why we're doing this, you'll find out later, maybe in 1311 or maybe in 1412 if you take it. But when calcium makes a bond with oxygen, it's an ionic bond, and it becomes CaO, so this is an ionic compound, which when you put it in water, and you probably are wondering why would you do that, which again you'll find out at some point later on, probably in 1412. When you put it in water, it rearranges and forms calcium hydroxide, which, because of the presence of hydroxide ion, is basic. So the bottom line, which you may want to just memorize, if you don't think you can remember what I just said, just remember this or memorize this. Metal oxides tend to be basic. In other words, if you make an oxide from something on the metal part of the chart, then it will tend to be basic. And what that means is it tends to have OH minus. And I'll take just a second to write this out. Or maybe a better word would be to scroll this out. Okay, next. The other one, non-metal oxides. would be things like, for example, carbon or phosphorus. So when they make oxides, they tend to make things like, carbon tends to make things like CO2, and phosphorus can make things like PO3, or the example they use here is this weird thing here, P4 tetraphosphorus dec oxide. So this maybe isn't the best example. You could also use PO3. Maybe that would be easier for you to see. So here are the oxides that they tend to make. Again, if you don't see why we're doing this, don't worry about it. And then when you put either of these things in water, they will rearrange. And this one will make carbonic acid, H2CO3, and this one will make phosphoric acid. Both of these, by the way, are present in Coca-Cola. Actually, carbonic acid is present in a lot of things. And then it makes H3. So obviously, this is carbonic acid and this is phosphoric acid. So they're both acids. So the bottom line is that when you have a non-metal and you add it to oxygen to make an oxide, and then you put it in water, it will create an acid. So, for example, H3PO4 will give up a proton. And I'm not going to write out the other part of it because it'll take forever. But it will give up H+. And also, of course, you'll be left with what's left over with the rest of this H3PO4, which will be H2PO4 minus. Next. Oh, before I switch it, so what you should try to remember here is just this part right here. When you have a non-metal oxide and you put it in water, it will produce an acid. So if you have to, just memorize that, but you should memorize this because it's probably going to be on the test. Okay, the halogens next. Fluorine, chlorine, bromine, iodine, they're the most reactive of the non-metals, the things on the right-hand side of the chart. If we go down a group, the radius increases as always, and also the electronegativity. Again, we'll study this in the next chapter. Anytime you go down a group, you become less electronegative. Don't worry about this as usual. Next. So halogens are powerful oxidizing agents, which means they're reduced themselves. In other words, they gain electrons, which we knew that, right? Because they have 7 valence electrons and they want 8. So they really, really want one more electron. They're nonmetals. All of them are nonmetals in this case, unlike 6 column. When you're at room temperature, the fluorine and chlorine are gases. So this one is going to be F2, and this one is going to be Cl2. Bromine is a liquid, and iodine is a solid, actually. They're all diatomic, so the bromine will also be bromine 2, and the iodine also. And they're non-conductors. That's something you should definitely remember. So nonmetals tend to be non-conductors of mainly electricity, which is what we're mainly worried about, but also heat. And then they're very reactive because they want more electrons. And to get the extra electrons, they have to react. They have very negative electron affinities. That is, they put out a lot of energy when they gain electrons because they're more stable. And then when they join together with metals, they produce things that are called salts, like, for example, NaCl. So the Cl here would join together with Na. The Na donates a proton to Cl. Na becomes Na plus and Cl becomes Cl minus. And you have NaCl, which is a salt, next. And then the noble gases next. What you should remember, they're all gases. They're monatomic gases, it's not like neon 2. What I'm writing here, if you can't read it, which you probably can't, is mono. They're monatomic, so they exist just like He, not He2, Ne, and so forth, not Ne2. That's what this means. They're all gases, at least at room temperature. And you can't see them, you can't smell them, okay? But they're not dangerous, so that makes it less dangerous. that you can't smell them or see them. I mean, because if they were dangerous, then that would be a bad situation. So they're used in situations where you have to have something very stable, like smoke detectors. Okay, so they're used in smoke detectors. They're used in fluorescent lamps for a different reason, and that is because when you bombard them with the electrons in them will go up to excited states and then drop back down. When the electrons drop back down, they put out light. They have very low melting and boiling points, obviously, since you can determine that or induce that because they're existing as gases at room temperature, and they have very, very large first ionization energies. They really hold on to all their electrons and don't want to let go, which means that they are very unreactive, and that is it. So what I'm going to do is wrap this up because I went long. So I'll stop here, and then we'll talk about this more with regard to the work problems. So let's just stop.